So you first decide, how close do I need to be to L? So we might decide we want to be this close. So this would be L plus epsilon, and this would be L minus epsilon. So we want to be that close. Well, since the limit does exist, we can see that from the picture, it does go to L. Then what this says is, once you tell me how close we can be, we should be able to go backwards now. So I should be able to come over here and find an interval about C. That's what the delta is. Delta says you got to be this close. Because you can see if I go too far away, if I go out to here, I can look up here and I have a function value that is outside that interval. And that's too far away. So, but if I get close enough to C, then everything should be inside that interval. And basically, graphically, we can come back here and say, well, that would take us to here. That would take us to here. And then we just kind of reflect down and say, well, I need to be that close. And I need to be that close. Such that if I am that close, then everything inside that interval will be inside the epsilon interval. Okay, and that's what this limit definition is saying. You tell me how close you want to be on the y-axis, then I could come up with a distance and say, okay, as long as I am this close, as long as I am within delta, C plus delta to C minus delta, as long as I'm contained inside there, then everything will be in there. And I can do it for any degree of closeness. I did it for just one particular example here, but you could do it for any amount of closeness that you want. And that's what the definition is saying. That's what the definition is saying. Is that you tell me how close you want to be, then I can figure out another distance on the x-axis so that should I turn out to be that close, that's all that inequality says, is I'm delta close to C, I'm within an interval of delta about C, then everything, every function image will go inside the epsilon interval.